Hello, I want to talk today about graph-based simultaneous localization and mapping, or graph-based SLAM, and introduce a so-called least squares approach to the SLAM problem using something which is often referred to as postgraphs. So this is a popular technique which you find today in most state-of-the-art systems out there that are designed to build a map of the environment and localize a platform within that map. And we're looking here to a special form of that, which is the so-called postgraph-based approach. That is an approach which doesn't use landmarks but reduces everything to the poses. So everything is kind of reduced to the poses, or landmarks are marginalized out. This leads to a graph structure which is actually rather easy to maintain, and is actually very flexible also in terms of the observations that you're including, and therefore became one of the standard tools when doing LiDAR-based SLAM, for example, or working with RGBD cameras or similar. So most of those systems which build maps of the environment which have a certain size, so which are not, let's say, a single room or something like this, typically use a graph-based or post-graph-based SLAM approach in the background in order to correct the poses and build a consistent map of the environment. And the goal of this lecture today is to introduce you to these graph-based SLAM systems so that you are in the end able to build your own system that performs the optimizations in here. And what we're using in order to do this is the technique called least squares that we just have introduced in the previous lecture. And so I assume you know how least squares work, and at least in a very basic setup. So Gauss-Newton is something that you should be able to explain or implement. And with this tool at hand, and with knowing how ICP works, or at least what the output of ICP is, you should be able to understand this lecture today. So within the typical SLAM paradigms, we are here in the graph-based SLAM approach, which is, as I said, over the last years became the most popular technique. And it basically is a least squares approach to SLAM. Of course, there are extensions using different error functions, robustified kernels, and things like this. But we are sticking here with the basics, which should allow you to understand how this graph-based SLAM actually works. So least squares, again, was an approach for computing a solution of an overdetermined system. Overdetermined means here that we have more equations than unknowns. Unknowns, in our example, are our parameters, where the robot is in the environment, which will generate us this postgraph. And the equations stem from our constraints, and constraints can result from observations or from control commands. And our goal is to find a configuration for those poses, for that postgraph, that minimizes the sum of the squared errors that are introduced by those equations, so by the observations, so that we have a configuration of these parameters or of these nodes in our graph that allows us to estimate where the robot is, so that the current configuration is as good as possible in line with what we have seen or experienced. And again, this least squares approach we apply today to the SLAM problem. So let me very easily introduce this problem. So consider we have a mobile robot like this guy here, driving around through the environment. And at distinct points in time, let's say every second, for example, we are generating a pose. And the pose is here explained or illustrated by those triangles. So the robot moves through the environment, and while it is moving through the environment, let's say every second, or whenever the robot moved more than 3 meters or 5 meters, that doesn't really matter here, we create a pose or a variable. And this variable describes the pose of the platform at that point in time. Pose refers here to the XY or XYZ location plus the heading information. So XY and the orientation theta in the 2D case, or the yaw pitch roll angles, for example, in the 3-dimensional case. And while the robot is driving through the environment, it creates these poses in this so-called pose graph. And between those poses, there are constraints. And these constraints result from the motion of the platform. So for example, you have a robot which counts the revolution of the wheels. Let's say it counts how often have the wheels been turned, and this allows the platform to estimate its poses. So let's say I'm the robot right now here. I'm creating a node at the current point in time. So I'm driving around, I'm turning my wheels for a certain amount of time. And then I'm standing here and creating a new pose, saying a new variable. And then there exists a constraint between the current pose where I am and the pose where I have been before. And this constraint results on how many revolutions do the wheels have. Did the wheels made. And so if there were, because the revolution of the wheels are related to the distance, for example, between those two nodes, so this allows you to say, okay, pose 2 is, for example, a meter away from pose 1. You're typically uncertain about those, about this information, because maybe it's 1 meter and 2 centimeters, or 95 centimeters, or 1.20 meters, or a little bit more to the right or to the left. So you see there are some uncertainties because this information is not perfect. So see those constraints as kind of soft constraints, which say, okay, pose 2 should be approximately 1 meter away from pose number 1. So I think you kind of get the information here. So the robot drives around, creates poses after different points in time or after things has traveled a certain distance. And then we have those constraints. And those constraints can stem from the odometry information, or the robot may even use a sensor, for example, scan matching or ICP, aligning consecutive scans in order to estimate its pose. So this generates this type of structure that we see here. And now the robot continues moving through the environment. At some point in time, it revisits a previously seen place. So it comes back to the same area over here. And this is one key element in the context of the SLAM problem, something we often refer to as loop closing. So the robot comes back to a previously seen place along its trajectory. And at that point in time, it can actually not create only these sequential constraints, but can also generate those constraints here to previous poses. How does that work? So this can work, for example, through an ICP approach. So we have introduced ICP before, where we take, for example, 3D laser scans of the platform taken at a previous point in time, so taken here or here, and align them with the scan taken from this location. And through the alignment of the scans, we can actually compute the relative transformation between those nodes. Something I was in the last lecture on the ICP lecture referring to as virtual constraints or virtual observations. And this is exactly those edges over here, or those constraints, soft constraints over here. So by revisiting previously visited or places where we've been before, or re-observing previously seen areas, we can generate these constraints between non-successive poses, these kind of loop closures, so to say. And so while the robot's driving through the environment, we are getting this kind of graph structure. So it's not a kind of chain of poses or a list as was before. It's really a graph structure that we now get here. And this is what gives the name pose graph, because we have a graph that consists of poses of these triangles. And so this graph is very central to the SLAM problem. Therefore, we also call it the graph-based SLAM problem. And we use it to represent our problem here. So this type of graph is the representation for our SLAM system. So everything in the graph that we have in there is important for the SLAM problem. We will use this information in order to compute a solution. So the graph consists of two things, nodes and edges. Every node in this graph represents a pose of the robot at a certain point in time. So again, it's typically a 3 or a 6 dimensional vector, depending if we are modeling a robot in the 2D space or in 3D. And then we have the edges, and the edges are kind of the relations between those poses. So they tell me, oh, this pose should be related to the other pose in that certain way. And this information can come from odometry information or from my sensor observation. For example, performing scan matching. So I can say the pose number 10 is related to pose number 11 by being 1 meter away, and at the same point in time you can say the pose number 10 can also be related to pose number 20 in a certain distance. And so this information is then being used in the optimization problem to formulate these equations that are used for the constraints. So every edge is connected to two poses and relates those two poses, either coming from odometry information or from my sensor observation, such as ICP. And in graph-based SLAM, we are building up that graph. So we build up this full graph of poses and constraints between poses. And then the goal is to change the location of the poses. So we're basically shifting and rotating those poses in the pose graph around so that we minimize the overall error, the squared error that is introduced by those constraints. So those constraints can be conflicting. For example, if I'm here and saying the next pose should be 1 meter away from that pose. And then I'm driving around, revisiting the environment, and come back to a previously seen location. And then, based on this observation, which comes from this, from relating those poses, this pose should be shifted a little bit. Okay? And then I have one constraint which says they should be 1 meter away, and the other one should be shifted in a certain way. And this leads to the fact that those constraints are conflicting, and I want to find the configuration of the nodes that minimizes the errors introduced by the constraints. So we just have also an example here how that looks in reality. So if we have a robot driving through the environment, so this was a map built by Patrick Pfaff, and what you see here is a map built from a laser scanner, where a 2D laser scanner moving through the environment, and this is just encodes the odometry information. So just estimating how the robot moved based on the revolution of the wheels. And you can see, actually, this map is extremely messy. You can't even deal with that. So you can see these are always the same rooms mapped at different locations. So odometry itself is typically not sufficient to build a good map. But what we can do now, we can actually generate this post graph in this map where we have been, and also relate all those constraints with each other. So we get something like this. So you see those lines over here, which represent the poses and also represent the constraints. So that means, oh, this pose should actually be over here. This pose should actually be over here. This pose should actually be over there. And so these are those constraints, and we now have a graph of all these constraints. And now we want to find a new configuration of those nodes so that the error is minimized, so that those constraints are actually fulfilled as good as possible. So we can, at that point in time, actually forget the map, which just was depicted in the background, and we are only interested in actually finding new configuration of those nodes, because those nodes correspond to the poses, and once we have the poses, we can actually build a map just based on the corrected pose information. Again, mapping was easy once we know the poses. So what the graph-based SLAM approach does, it takes this thing here as an input, this graph structure, and performs a least square minimization so that it finds new configurations of the poses that minimize the errors introduced by the constraints. And this will lead then to a map that looks like this, where all the trajectories are kind of now overlaid with each other, and the quadratic error introduced by those constraints is minimized. So that when I take this pose information and then render a map, just performing basically mapping with known poses, building an occupancy grid map, I will actually get an information which looks like this. And this is now a consistent map of the environment. So you can see here also this room is always at the same place and not spread all over the place. And this process of turning this graph into this graph, this is what we're talking about, performing the error minimization, so to correct the trajectory of the platform, that we then can use this trajectory to build a map of the environment. Okay, so I have to tell you that this is only one part of the SLAM problem. This is what is typically called the backend or the optimization part of that. In reality, of course, there is more involved in this if you want to build a real-world SLAM system, because you need to turn your observations into constraints. And this is something we typically refer to as the front end. So taking the raw sensor data and turning the sensor data into constraints is kind of the front end, and taking those constraints and optimizing the graph and returning the corrected poses, this is what's often referred to as the back end. And in reality, this is an interplay between those two. So the front end relates poses with each other, then it's being optimized, then this optimized map information is used to make new data associations. So in reality, there's actually an interplay between these front end and back end thing. But here we are only looking into the back end part, so into the optimization part, and you can envision the front end part basically as the ICP algorithm that we've introduced. The ICP is typically used for laser-based SLAM systems as a front end to generate those constraints, and the constraint is here actually the relative transformation, so the outcome of the ICP algorithm, this rotation matrix and this translation vector, and they are basically forming a constraint together with some uncertainty information. And there's a little bit more to that than just vanilla ICP in order to do that well, but for the moment you can imagine we are running an ICP based on a laser scanner, for example, which gives us the relative transformation between poses. This is kind of this front end part here, and we are using this raw data or this constraint data in order to build the graph and or to represent the graph and optimize that graph. Okay? So the graph consists of nodes. So the individual triangles here, these blue triangles, every of those triangles represents one node, x1, x2, x3. So there's x1, x2, x3, x4, x5, and so on. And so the overall graph represents all n nodes, represents x, and this is simply the all nodes put together or stacked on top of each other. So each xi is a pose of the robot at time ti. So at a certain timestamp. So we assume to have unique timestamps being here. And if we have a constraint between two poses, from a node xi to a node xj, then this is a constraint. This can result from odometry information or from these virtual observations. And these are those edges over here. And we will now look a little bit into that, how we actually describe those edges. And then once we have those edges and can interpret them, then we see how we can actually perform the error minimization task using the idea of least squares, or in this case Gauss-Newton. Okay, so an edge exists between two nodes if the robot moves from xi to xi plus 1. So this is now a consecutive edge. And this is an edge which can be generated from odometry or also from incremental loop ICP, so matching the current scan against the next scan. But for simplicity reason, just assume right now it's odometry. So just by counting the revolution of the wheels. So we are here, the robot is currently here, it moves forward, and then based on the odometry information, it can estimate where it should be, given the robot or the motion follows the kinematic model that the robot has about itself. And this is basically the information, like a motion model that we're using. So if you think about the previous lectures, this is basically counting the translational velocity, the rotational velocity based on your steering, such as differential drive or Ackermann steering, and that tells you how much you should have moved if everything looks good. And from a probabilistic point of view, that's basically a mean estimate of where you have been moving within the time difference from I to I plus 1. And this typically comes from odometry information. So this is a transformation which tells us how xi can be seen, or how xi plus 1 can be seen from xi. So see this as a transformation. So how do you transfer one pose and the other pose? So relative pose information. An edge can also exist between two arbitrary poses, so not I and I plus 1, but I and j, where j is different from I plus 1. And then we typically need to relate this information with each other using the sensor data. So as an example, so consider this now as a 2D illustration. So we have our robot at xi sitting over here, and this is the scene it is observing with its laser scanner. And then at a position xj, it's here, and it's observing this part. So by relating these black line and this blue line, treating this as a scan and overlaying them with each other, we can actually generate kind of a virtual observation by saying we can have an idea where xj should be as seen from xi. Although we can't really see xj, we can't really see where the robot is in the future. But by relating it to the environment that we are seeing from both locations, we can actually generate something which we call a virtual measurement. It's nothing else than the result of the iterative closest point algorithm in general. So again, we see this kind of treat this as our reference frame, and by matching the black line and the blue line, we are basically moving the blue one over here, and then if we know where the blue one is, we also know where xi is in this reference frame of xj. So by constructing this kind of virtual measurement through an alignment procedure such as ICP, or if you think about vision, this could be computing the relative orientation, for example, using the 5-point algorithm or the 8-point algorithm for image features, but we are restricting ourselves here for the simplicity to ICP, then we would get this type of alignment. So you see here the black and the blue lines are aligned on top of each other, and this allows us to relate the poses xi and xj with each other. And then this transformation from xi to xj can then be seen as a virtual measurement about the position xj as it would be seen from xi. So if xi could see the robot at xj, it would be the pose of the robot relative to its own pose. But as we can physically not see that, we do this through the relation of the environment. And again, this is a full transformation between those two poses. So it's not just kind of a distance vector or something like this. It's a full transformation that we can transform the pose xi to the pose xj, or the other way around. So how do we encode those transformations? We typically use things like homogeneous coordinates for doing this, or there are other ways in which you can do this, but at least for formulating it and writing it down in here, I will be using homogeneous coordinates because this is actually very easy to do. So just as a reminder, homogeneous coordinates allow you to express chain transformations like translations and rotation in a very elegant way. So, and then everything which is here written in capitalized characters you should see as a transformation. So this is kind of the transformation, basically the of the pose xi. I'm seen as a translation and a rotation in a global reference frame. So this is a homogeneous matrix. This is also a homogeneous matrix representing this pose xi and xj. And if I have those matrices, I can here invert the matrix xi and multiply the matrix xi plus 1 to it. Then this is a relative transformation. Where is xi plus 1 as seen from xi? And the same holds here. Xi inverse xj means the node, how the node j sees, how the node I sees node j, so how j would be seen from node I. So just as a very short reminder, in case you have forgotten about homogeneous coordinates, just a few words what that is. Homogeneous coordinates are a different coordinate system, or coordinates which are typically used in projective geometry. It has some nice advantages of being able, for example, to express points which are infinitively far away and those things. But that's not kind of the reason why we are using it here in the lecture. We're using it here in the lecture because in this homogeneous coordinates, a single matrix can represent all affine or even projective transformations. And that's attractive for us because we will be using here rotations and translation, so rigid body transformations, which are a subset of those two transformations, through matrices. And so that means we have a matrix that represents a translation, and we have a matrix which represents a rotation, and we can just multiply those matrices in order to chain the transformation after each other. And that makes it very elegant in order to write it down. And this is one of the advantages of homogeneous coordinates, that they typically simplify the math, at least for us, when we need to write that down. So how does it work? I just have a short example, and if you need more information about this, I recommend you to watch my lecture on homogeneous coordinates. But just as a very short reminder, if you want to represent the n-dimensional space, like the three-dimensional space for us, then homogeneous coordinates use one dimension more, so n plus one dimensional space. So for us it would be 4 dimensions for modeling the three-dimensional space. And the vector in homogeneous coordinates, let's say x, y, z, is extended by a new dimension x, y, z, and the next dimension, which is 1 in this example. There's a mapping from the Euclidean space to homogeneous coordinates. And there's also backward mapping, which we say we have the 4 coordinates, x, y, z, w in this example. And then we take the last dimension and divide all other dimensions by that last dimension and then drop the last one. So we go from a 4-dimensional vector to a 3-dimensional vector, dividing all the elements by w. And so it's kind of a normal form of normalization. And if we do this forward-backward mapping, then we can actually express translations and rotation in an elegant way. So a translation can then be expressed in a 4-dimensional matrix, which has 1s on the main diagonal. Here everything is 0, and those 3 dimensions are the translation in x, translation in y, and translation in z. And the rotation can be expressed by a 3D rotation matrix, the standard rotation matrix as you know them, here in this upper 3x3 block. And so this is a 0 vector, and this is also a 0 vector and a 1. And so by having this rotation matrix in homogeneous coordinates and this translation in homogeneous coordinates, we now can multiply this translation matrix and the rotation matrix with each other, and then have a translation and rotation expressed in one single matrix. And that's something you cannot do in the Euclidean space, and but it's very, very elegant for writing this down and chaining those transformations. So if we go back, for example, something like this, to express this in Euclidean coordinates is much more difficult. And here it's very easy to see. You take the pose of x, the transformation which encodes xi, and you basically invert it. So you can, just by inverting this 4x4 matrix, you're actually inverting the transformation and multiplying to that from the right-hand side xj. So what you can see then, that this is actually the node xi as it would be seen from the node xj. And so that's what we are using here. In addition to this, our constraints are affected by noise because we have observations. So for example, odometry is typically less accurate than using your sensors information if you think about a laser scanner, for example. But even your laser scanner data is affected by noise. And so the transformation that you're actually computing are not perfect. And the information matrix omega ij is the information matrix related to the constraint between the node I and the node j, and encodes the uncertainty that stems from the observation. So how much do we trust that information? And we may have a sensor where this is the same for all constraints, but we may have different types of sensors or different situations in which the sensor is more accurate in a certain setup and less accurate in another setup, and we can actually use this information. So the higher the value, the larger the values in this information matrix, the more information we have, the smaller the uncertainty. And the bigger it is, this omega, or the values inside omega, the more this edge matters in the optimization. So if you remember back the least squares, how it worked, then this information matrix is basically a weighting factor for your error. So if you have a constraint which has an information matrix which is larger, which is, let's say, has a value which is twice as large, it will count more, twice as much inside the optimization. So this edge information is actually important in order to take the uncertainty into account. And so then there are questions: how would you expect this matrix to look like if you compare scan matching done with ICP to odometry information? So which is more accurate or less accurate? That's one relevant information you should be able to figure out. The other thing which would be relevant if you think about ICP and you make this scan alignment, and you have a robot which drives along a very, very long corridor, and this corridor is, let's say, very sparse of features. It's just long walls. How would this information matrix look like? And thinking about those questions allows you a little bit to understand if you can relate your observations and the information you can extract from your observations with this graph construction here. So in the first setup, related to the first question, your sensor information, at least from a laser range scanner, is typically better than the odometry information that you have. Again, it depends how much engineering you put into your odometry information or your laser scan information and what you know about the environment. But at least for a lot of, let's say, standard indoor mapping systems, you will actually trust your laser scanner quite a bit more. So you expect the covariance matrices to be smaller. That means the values in the information matrices to be bigger. This may be different if you have a less accurate scanner or you have a lot of motion or movement dynamics in the environment, but put a lot of engineering into getting your odometry information right. Maybe having redundant systems, taking multiple wheels into account, a very good dynamics model, for example. In case of an autonomous vehicle, autonomous car, you can invest quite some brain power into your odometry system that you can trust odometry also more. Regarding the second question, how would these information matrix look like, or the corresponding covariance matrix look like in a long featureless corridor? So what does it mean? A long featureless corridor means the robot can localize very precisely with respect to its right and left hand side, because you see the walls of the corridor. So you have very small uncertainty with respect to your motion to the right and left hand side. Also with respect to your orientation, given that you have very long walls, you can typically align the scan very good with respect to a corridor. So you shouldn't get much drift to the left and right hand side. But what you actually is hard to estimate is where you're moving along that corridor. So you have a very high uncertainty along the main axis of the corridor. So you would expect to get in covariance matrix, which is very narrow to your right hand side, but very long and stretched along the main axis of your corridor. And so if you inspect your information matrices or covariance matrices of your graph, you can actually see something about what information did the sensor actually tell you. And this then is an important information how the uncertainty actually propagates in the end through your graph, through your least squares problem. Because if you have very large uncertainties along certain dimensions, this will also lead to a large uncertainty along this line. Okay, so let's have a look to the post graph and look to all the information that we have. So what we see here is a very, very tiny post graph. We just have kind of two nodes over here, xi and xj, so you can see this basically is cutting away everything else. And what we have is we have a current configuration of the nodes. So, and this is those two positions here, just let's say in the 2D plane, just to make it easy to illustrate that here. So this is, we think this node sits over here and that node sits over there. And this is the current configuration of the graph. Now we have a constraint between those two because there's a common observation, for example, from ICP. And let's say this is what the observation looks like with the corresponding uncertainty here illustrated through a covariance matrix. So this is basically, this is the position where if I would sit in xi, would expect xj to be. And you can see here that there's actually a mismatch between what the observation tells me and what the current graph configuration tells me. So this is an error that we are computing, and this is the error that we actually want to minimize. Okay, so this thing should be brought to 0 over all constraints, of course. And this edge here is basically represented by the kind of the mean observation here encoded as Zij and an information matrix, which is here illustrated through the inverse of it, through the covariance matrix. And so this is the information we store in every graph. So every observation will lead to such an edge. And what we're actually trying to minimize, we want to shift the configuration of those nodes in order to minimize this error. So in this case, it means xj should actually move here in order to bring this error towards 0. And of course, the problem is it's not just one edge which is involved in this, otherwise it would be easy to satisfy this constraint. We have the goal of doing this for all our constraints. So this was just kind of one example, but of course the whole graph consists of those constraints. And what we want to do is we want to minimize the overall sum of that. And this is where the least squares approach or the ideas of least squares actually kick in. So we can go back and to our previous lecture and think, okay, this is now our squared error function. We have our error vector relating the constraint I and j with each other, the information matrix, and again the error term. Or we can kind of rewritten this in a short version where we just put the vector x in here, the whole state vector. So this was the way we were formulating this before in the previous lecture, where we say the error or the error vector here depends on the state variable x. What is important now, or the difference here in the SLAM problem, we actually can formulate it in that way that we say not the whole vector x depends actually on this error term, but only xi and xj. That means only the node xi and node xj, so those two contribute to this individual error term. And all the other state variables do not matter for that single constraint. And this is something, an information that we will later on exploit in order to solve the SLAM problem in a very efficient way, or in an efficient way, because we know that the individual error terms only depend on a very small number of variables. And that's something that we will exploit later on. On the first question, we may look like, what does the state vector actually look like? So if you now want to sit down and actually implement our system, how should that actually look like? And what we need is our state vector x is simply the concatenation of the poses of the graph. So every vector, so one vector for every node of the graph, and we just kind of concatenate them with each other. So it gets a very, very, very long vector. And it's always kind of x, y, theta, x, y, theta, x, y, theta. It's always the x of the first node, the y of the first node, the orientation that the robot had when being there, and then for the second node, x, y, theta, x, y, theta. Or, if you're doing a three-dimensional world, x, y, z, yaw, pitch, roll, for example. Or another representation on how we could represent the six-dimensional degree of freedom poses. Okay, so we have that. We know what the state variable looks like. So the next thing is, let's look into the error function. How do we relate those error functions with each other? We said, yes, of course, the individual poses xi and xj should pop up, and also the observation should be taken into account. So the result of the ICP approach should play a role in here. And we can formulate a single constraint now in the following way. So what do we see here? So let's just look only first to this part over here. So the first thing. So we had xi inverse xj. So this is kind of how xi sees xj, or how xj is seen if the center of the coordinate system would be in xi. So you can think of seeing yourself standing in xi and then see where xj actually looks like. So this is what this information provides, and it's directly, very easily computed through the homogeneous coordinates. And then we have an observation. This observation z tells me how xi sees xj. This is a result of the ICP algorithm. So the transformation that results from ICP, so the rotation matrix and translation vector. This is this z. And then I invert this z and multiply it here to the configuration of the graph. So the whole block here, you can see what's the difference between the poses with respect to the graph, and what's the difference of the poses with respect to the measurement. And so one is kind of, you can see this as kind of a forward transformation on what the graph tells me, and then a backward transformation on what the observation tells me. And then I need to look into the difference between where I started and where I end up, and this is basically my error function. Okay? So that's what actually happens in this part over here. So the relative transformation according to the graph in one direction, and then the inverse of the observation, so turning this around and going back in order to compute the difference between them. And then there's a function called T to V over here, a magic function. T to V means transformation to vector, and V to T means vector to transformation. So this is basically just a mapping between a vectorized representation, vector, so x, y, theta, for example, and the transformation expressed in homogeneous coordinates. So it's just kind of a forward-backward mapping from this 3x3, or from this from this vector, so whatever 3x3 homogeneous matrix into a three-dimensional vector with x, y, theta, so that the transformation consisting of a two-dimensional translation vector and one rotation angle encoded in a 3x3 matrix is put into a vector. And because this here again is a transformation matrix, and we need to put it in vector form in order to put into our least squares problem, and that's what this T to V stands for. So this gives us here in this example, if we are doing this in the 2D plane, a three-dimensional vector with x, y, and one orientation constraint. Or we can express this also not just for a single constraint, but we could express the same also for the whole state vector. And then, of course, only those components matter where there is actually an involvement. And it should also be cleared what happens, when is the error of 0, when does the error take a value of 0. And this is exactly the case if my observation is the same than my relative graph configuration. So if what the graph tells is exactly the same what my observation tells me, then this equation holds if I would multiply and then you can actually see that if I would multiply here z inverse from the left-hand side, so the inverse observation, and this term is the same, then this is the identity matrix. So that means if the transformation of going the transformation through the graph and backwards through the inverse of the observation gives me the identity matrix, means there's no transformation mismatch. And this would then give you the identity matrix would be mapped through this function to 0, 0, 0. So a 0 error vector. Okay? So the only thing we need to specify is how do we get z, and this is something that our ICP, that's a result of the ICP algorithm, just put into a homogeneous vector, and these are just the poses in my post graph expressed in homogeneous coordinates. And with this, we actually can look, okay, let's rebuild Gauss-Newton. How did the overall error minimization procedure look like? So the first thing we need to do, define the error function. That's something that we just did. What we then need to do, we need to linearize our error function, just because we need to perform local linearizations. And then this leads to the quadratic form, where we compute the first derivative and set the first derivative to 0. This gives us a system of linear equations. We solve this system of linear equations. We get the update of our state, and then we iterate this process, restarting here at the linearization until we have converged, as we discussed it in the lecture before. So, just as a short reminder, this was our error function, the original error function, which we now need to linearize. And again, if you think about this homogeneous transformation matrices, you may remember in a rotation matrix there are sine and cosine functions popping up. These are nonlinear functions, so you need to perform linearization and linearize that thing. And that's where you need to sit down with a piece of paper and actually try to perform this linearization. Or if you use another error minimization framework, you may, some systems do compute this automatically or numerically for you, depending on how good your tools are, but otherwise you have to do it by hand. That means you need to compute a matrix. This is your Jacobian matrix, and every element of the Jacobian matrix consists of the partial derivatives of deriving the your error function or the individual dimensions of your error functions with respect to the individual dimensions of your state vector. So you derive it in this case with respect to x1, x2, x3, and so on and so forth. And here we have to look a little bit into the details, because how that looks like actually has a very big impact on how efficiently we can actually solve the state estimation problem later on. So the first question we need to answer, does the error term depend on all state variables. So again, this is an error term EIJ, that means for one single observation. And thus it depends on all state variables, so my whole state vector. It clearly depends on the state vector, but does it depend on all elements in there? And within the SLAM problem, this is not the case, because we said that this error term only relates the two variables to which this edge is connected in our graph. So there are just two poses, namely the pose with index I and the pose with index j, on which this actually depends on. So no, this depends only on xi and xj. And this will play an important role because this has an impact on the structure of the Jacobian that is involved in this. You may think about this if you have a function which depends only on a small subset of variables. If you then derive this function with respect to the variables, then it will have a lot of zero elements, namely where if a function doesn't depend on one variable and you derive with respect to this variable, it will be zero. And this is a key insight because this leads to the fact that the Jacobian will actually be zero nearly everywhere except for the elements which are related to the variable xi and with respect to the variables xj. So if you think of, you have a, whatever, 10,000 dimensional state vector, and you have a constraint just between two poses, then only those two poses will be related with each other, and the all other 10,000 minus 6 dimensions will actually be zero. So your Jacobian will be a large vector which consists only of zeros and just has a very small number of elements which are involved in here. So the partial derivative in this Jacobian of the error function with respect to all the parameters is basically you have here all your error vectors and your state variables will be zero everywhere except of those blocks which are related to xi and those which are related to xj. So in this case, for example, if xi is in 2D plane, it's x, y, and theta, there will be 3 elements here which are non-zero, 3 elements which are here that are non-zero, and the rest will be completely zero. So we just have 2 blocks of variables here, we call them aij, bij, which are non-zero, and all the rest is zero. And this is kind of a key insight because this leads to a sparse Jacobian, which will also have a big effect on our H matrix later on. So, Jacobian and sparsity. If our error function depends only on the variables xi and xj, that means all other elements, which are x1, x2, x3, x4, x5, and so on, which are not I and j, are zero. And these are illustrated by these blue blocks over here. So these are all the blocks which are zero. And we just have these small blocks which are non-zero. And this is kind of a key insight in here, that we have this huge Jacobian. Everything is zero in this Jacobian except those 2 blocks. And this is the key insight. So it's one of the most important slides in this slide set, having this insight, because this allows you to solve, let's say, real-world SLAM problems in an efficient manner. Why is this the case? Why is this so important? This can be illustrated by the fact that the Jacobian has a key role for computing the elements b and h, which I need to compute in order to solve my system of linear equations. So my vector b and my matrix h consist of elements which involve the Jacobian. So for the H matrix, very clearly you can see the Jacobian popping up twice here, and also for the B matrix you see the Jacobian being over here. So as we will see, the sparse matrix in the Jacobian will also lead to a sparse matrix H, and this is one of the key reasons why we can actually solve them in an efficient manner. And I want to illustrate that now to you through a small illustration. So what you have here is this vector b. So the vector b is a vector, and everything which is shown in blue are zero elements. Everything which is shown in red are non-zero elements. So I have this vector here. So the vector b is this vector, and it consists of my Jacobian transposed. So now it's a very long. So these are the dimensions of my state vector. This is my j. multiplied with an information matrix, in this case, for example, a 3x3 information matrix, and then my three-dimensional error vector. And this will lead, by multiplying this, to an error vector which is 0 everywhere and has only non-zero elements at the blocks referring to xi and the blocks xj. So for one constraint, this vector b is actually sparse. Something very similar holds for my H matrix. So in my H matrix, I see my Jacobian transposed here, my other Jacobian here, my information matrix, and I can see by multiplying those with each other, I will get a big matrix which is basically 0 everywhere except of 4 blocks. And these are the blocks II, JJ, IJ, JI. So these are the elements. So those are identical, and those 3 are different, so just those 2 are identical. And these are all the non-zero blocks. Okay, and this is for one constraint. So one constraint filled with H matrix at 4 different blocks, and the B vector at 2 different blocks. So only at II, JJ, IJ, JI, this matrix will be filled. But this is for one single constraint. And now we need to see what happens if we actually sum those elements up, so sum H up and sum B up over all constraints that we have. So if we take multiple of those vectors together, we will actually see that we get a fully dense vector B. So all elements of B will be filled because all the nodes will have some constraints, and so the whole vector will actually fill up. It's however different for my H matrix. So again, I have n squared elements in here, and always 4 for every constraint will be filled. So by adding all of them up, I will typically get a matrix which looks like this. So I have direct constraints here on the diagonal, which are the constraint, and also the direct off-diagonal blocks, because it relates how the current pose and next pose are connected with each other. And I have a couple of elements in the off-diagonal elements, which are basically my loop closure constraints. So where a node xi is connected to a node xj, which are not sequential. And so this matrix can be seen as kind of an adjacency matrix of that graph, which tells you what the connections in your graph actually are. And the key thing is this matrix is typically not dense. It's typically a very sparse matrix. Typically, the larger the environment, even the sparser this matrix gets. It's quite clear from the intuition point of view. If you have, for example, a robot navigating around, inspecting a big environment with hundreds of different rooms, inside the room, you only see the room. You never see another room from inside that room. Maybe from the corridor, you can see into a few rooms. And so all the blocks, the places in the environment are very decoupled and can only be seen from the same places, and not from all places can't see all other places. And therefore, this leads to a very sparse matrix. And this is one of the reasons that this matrix is sparse, why we can actually solve an even potentially very, very large linear system in the end in an efficient way. So the key thing in here is that each edge corresponds to this linear system, and for the vector B it looks like this, that we have 2 blocks which are non-zero, but by adding all of them up in the end this will lead to a dense vector, but we need to build this up by, for every constraint, adding in 2 places or in 2 blocks of this vector new elements. And for the H matrix, it's the same thing. I have this H matrix, everything is 0. There are just 4 blocks which I need to fill in this matrix xi, in this matrix at the positions I, jj, ij, and ji. And so this matrix H will be a sparse matrix. So it makes sense to also represent it as a sparse matrix. And depending how you do this, you can either use a mathematical toolbox, which already provides you with sparse matrices, and then you don't really need to care about it, or you have to implement it yourself, and then you need to make sure that you fill the corresponding elements in this block. So again, the key thing is an edge ij contributes only to the ith and the jth block of B, and the blocks ii, jj, ij, ji of H, which leads to an overall sparse system. And we can then use actually sparse solvers to do this. So there's a variant of Cholesky decomposition called sparse Cholesky decomposition, which is explicitly designed for sparse matrices and is much, much faster than the standard Cholesky decomposition, and also holds for other techniques. There are optimizations of most of the algorithms for sparse matrices because a number of operations which need to be done is much smaller and can be done in a much more efficient way. And this is kind of the reason why we are at all able to solve these systems in a reasonable amount of time. So you can also, if you want to build up these matrices on your own, again, you have your state vectors of your increments, you have your coefficient vectors of your b's, and then your normal equation matrix will consist of these small blocks. And now we have kind of this har bar over here to represent the individual blocks of that system which is built up. And then you just need to make sure you fill for every constraint the right blocks of your linear system. So what you would do if you build your linear system manually by hand, for each constraint you compute this error vector. For each constraint you compute the Jacobian, but of course you don't compute the Jacobian everywhere, only in the blocks where you know it is non-zero. So you only need to compute this Aij and Bij. The rest you don't have to touch because you know it is zero anyhow. And then you compute your, for B and for your vector B, the increments and add them up at the corresponding correct locations Bi and Bj. So these are the corresponding blocks in Bi and Bj, where you need to add these small blocks on top of it. And the same holds for your normal equation. So only compute those small blocks. So these are all low-dimensional blocks. There's these small ii, jj, ijj, I blocks, and you just need to add those small blocks to your matrix. So that means this is not an addition of a whole large matrix. It's just these small blocks that you need to add at the correct locations. So if you do this, if you build up the system on your own, you need to make sure you add the constraints at the correct positions in your matrix. But once you have that, you have your matrix actually built up. And then you can run your optimize function, which then turns out to be very easy. You say, while you're not converged, and the convergence can be whatever the size of your update, you build your linear system, your matrix A and your matrix B, exactly with what we have written on the previous slide. And then you run your sparse solver, which should solve h times delta x equals minus b. And this you can use Cholesky decomposition, as we have briefly sketched last time, but now you would use sparse variant of Cholesky decomposition. But that's something that happens to be very transparent to you if you use the corresponding sparse matrix classes in your mathematical toolbox. And then you can say my new configuration is my old configuration plus my delta x, so my update from the previous initial guess. And then I'm repeating this process while I'm converged, just building the linear system, solving it, updating the state vector, and iterating until I'm done. And then I come up with a new configuration x, which is now the new configuration of my graph, which minimized the sum of the squared errors over all constraints. And this is then the result that you can use in order to build the map of your environment. Just take the poses as they are, what is the best estimate you have, and then basically run a mapping procedure based on those poses and build a map of the environment. That's what's typically done. So you correct the poses first and then use the poses for your mapping algorithm, which is not a SLAM algorithm anymore. And then you're done. Okay, at that point in time, I want to show you a very trivial example. Typically, I do that on the whiteboard, but given that I don't have a whiteboard here, I just want to go through it anyhow because you see a few things you may have not taken into account before. So this is a very, very trivial example which just consists of two nodes in a one-dimensional world. So there's nothing that can go wrong, you would think of. So you see it, we have a node xi and xj, and we assume that there's one observation about them saying x2 is a meter away from xi. Okay? So we have our state vector consisting of x1 and x2, we just have two constraints. We initialize them both with 0, 0. Let's say this is our initial guess. We assume we don't know anything about them, we both put them into 0. Okay, Z12 is exactly our observation, and our observation says the node 2 should be 1 meter away from the node F1. So and this is this Z12, our actual observation, how far 2 is away from 1. Then we have an information matrix over here which tells us how certain we are about that. And then we can use this to compute our error. So our error function is our actual observation, in this case, minus our predicted observation. So our predicted observation is simply the distance between the two nodes, x2 minus x1. In this case, initially this is 0, so we have our observation is 1, minus 0, because we initialize them in exactly the same way, which gives me an error of 1. So my error E12 is 1. Then I need to compute my Jacobian, so I need to derive the corresponding error function with respect to both variables, and then of this error function, and of course I get a linear term with respect to x1 and x2, because if I need to derive this equation here with respect to x1 and x2, this will give me the values for x1, which is positive, because I have two negative signs over here, which turn out to be positive, and will be minus 1 with a derivative with respect to x2, because this is a negative x2 term derived with respect to x2 leaves minus 1. Okay, then I have my Jacobian, and then I can compute my B vector. So my B vector is my error vector times my information matrix times my Jacobian. So it will be a vector 2 and minus 2. And I can build up my H matrix, which is J transpose times omega times J, which will give me a matrix which looks like this and contains of minus 1s and 1s. Okay, now I have my H and I have my B. Now I can solve my system of linear equations. So it means I need to, in this simple example, let's say invert the matrix H and then and multiply it with X, and then I should get my update. But now it turns out that I have a problem. You know, to invert the matrix, it only works if the matrix has a determinant which is non-zero, right? So, but if I look to the determinant, its determinant here can be easily computed. 2 by 2 is 4, minus 2 by minus 2. This is also 4, so it's 4 minus 4 is 0. So, as a result of this, this matrix has a rank deficiency, and I actually can't invert it. So what went wrong? What's the problem that we have here? Why is it not working, even for this super trivial example? And what turns out to be is that the constraint that we have here is a relative constraint between the two nodes. It tells you how far is x2 away from x1. And so it only tells us something about the relative configuration between the two. It doesn't actually say us where 1 is actually and where 2 is in a global reference frame. So we basically miss the reference frame. It's also something which is called a gauge freedom that we have. And what we need to do is we need to fix one of those nodes. So we need to say, okay, let's take node number 1 and fix node number 1 to be 0, for example, or to be 1 or to be 2, whatever. And then we need to update our system to reflect that, and then we can actually solve that. Okay, we can do this in a very easy way by enforcing a constraint that the update on the first node should be 0. So there should be no update on the first node. It basically looks like a Gaussian distribution or a constraint of a Gaussian distribution which fixes the first node as the reference frame with a certain uncertainty. It's like a prior node that we add. And we can add this prior node as an additional constraint to our H matrix, which is just a matrix that has 1 here and is 0 everyone else. So it basically puts this delta x to 0, so no shift of the first node. And if we do this, then we can actually invert this matrix, because then it's not a rank deficiency anymore. Then this element is 3. We have 3 times 2 is 6, minus 4, 2, so has a determinant of 2, so that looks actually good. We can invert this matrix and then actually get an update which says the node 1 should not be updated, and then node 2 should be updated by 1. And then we have our configuration 0 and 1, which is the one that actually corresponds to the observation, because the observation said we are 1 step away. So this was, again, a very, very simple example in order to do this. But the insight that we need to add a prior or fix a coordinate saying is something that we should not forget. So we saw that this matrix is not full rank after we have added all the constraints. And even if we add more constraints, we will suffer from the same problem always, because we basically haven't fixed the global reference frame. This only changes if we have an additional sensor like a GPS receiver, for example, which fixes a global reference frame. Then this problem is automatically be solved. And otherwise, we need to set one of those nodes as our reference frame, for example. So we may use the first, or node number 0, and add a prior information, say, okay, this should be 0, 0, 0, or this should define my coordinate system. And we can do this by adding a constraint to pose number 0, which could look something like this, that pose number 0 should be, the transformation means I have a prior node, and this prior node should be fixed at x0. So basically, don't move x0 and do everything else with respect to x0. That's one way we can actually do this. And if we add this prior information to it, then we can actually run our least squares approach, get a solution, and build a graph-based SLAM system. And one example how this system is actually running in action you see over here. So this was also a video I've showed in one of the initial lectures. You see a robot moving around. Let me stop the video for a second. What you see here in the zoomed in view is a small robot, the map it built so far in the local view in the current laser scan. And here you see also the map built so far, so black are obstacles, white is free space, and it's actually moving around through the environment and just adding one after the other. And what you will see in a few seconds is that before, okay, let me check that here. So the robot here comes back to a previously seen place. And what you can also see, it's maybe a little bit hard to see in the video, but if you would zoom in, you can see that there's a certain mismatch, a small offset between the map built when the robot was starting and the map built when the robot was actually driving back. And you will see this map shaking in a second. And this shaking is a result of this optimization process, because we get new observations and the least squares approach shifts the nodes so that it minimizes the error introduced by those observations. And if I kind of restart and rerun the video, you saw it shaking a little bit. It will happen now again when the robot re-enters the map. You see kind of the map shaking a little bit. The more loop closes it has, the smaller this effect is, because the corrections have already been taken out. But whenever this happens, you actually see small corrections and the map is realigned. And this is the result, or the visible result, of the least squares approach that is actually running behind that. So this is a result of a full SLAM system which runs ICP, registers one scans against the next scan, and builds up a graph, and also looks for loop closures. So whenever the robot is kind of close to a map it has been before, there's basically an ICP running and see, do we find actually a good match? And if so, we add loop closure constraints to this. And then you can actually build a simple laser-based SLAM system like that. This was kind of the basics of this approach. And now I want to go also a little bit into talking about a few things which are important for you, which also are related to, for example, estimating the uncertainty and so on. So we assume that the values of certain variables may be known a priori. So there may be some information that we either want to impose to such a system or that we get an additional information where something should be fixed and should not move anymore. So how do we actually do that we kind of fix a certain number of variables? So it's similar to the prior that we add. We can add one of those prior nodes, for example, saying, hey, you guy should actually be fixed here. But the problem is it's just a soft constraint. It's not really a fix. And what can happen is if we have other constraints that they actually pull away this node, and we cannot ensure that a certain variable has to have a certain value. But we want to be able to do this. So we want to fix one variable. As a result of this, this variable actually should not be optimized. So it should actually disappear from our linear system. Because if it's not in the linear system anymore, there will be no update on this variable, and all the other variable actually should be constrained on that. So we kind of want to have it as a condition. It's like a condition that given this node take this value, how does the rest actually look like? And we can do this by actually constructing the full system and then simply suppressing the rows in the column that correspond to this variable in order to fix this variable, and then solve the linear system. If you think about it, okay, why can we actually do this? Why can we just kind of suppress the row in the column, just take it out of this matrix, and solve, and of course also from the x variable and the b vector, and then solve our system, and then we actually fix the variables. This is a result, why we can do this, results from the conditioning of Gaussian distributions. And if you think about the information space you're in, so when we studied the information filter, you may have seen that the conditioning in information space means I can just take out, just cut out a part of my information matrix and just ignore the others. And this corresponds to a conditioning operation of the Gaussian distribution. And our H matrix is an information matrix of our overall problem, of all the constraints taken together. So by taking out, cutting away, let's say, a few rows and a few columns, I'm basically conditioning the system on these, that these variables are fixed and cannot be moved, and all others has to be constrained based on the current variable that those system has. And therefore, I can actually do this. I just can cut out the corresponding rows and columns from my H matrix, solve it, and this means I'm actually fixing those variables that I've cut it out. And this is something that you can actually use if you want to constrain something. The next thing I want to look into is actually the uncertainty related to this. So I told you right now that this H matrix is an information matrix for my overall system. So it provides me with information about the uncertainty of the overall estimate up to the linearization point. So given the linearization point, given we are converged and we are under the approximation of this linearized function, this is an information matrix. So in order to obtain the uncertainty, my covariance matrix, I actually need to invert H. And invert this matrix, and then I have a covariance matrix, and this covariance matrix tells me something about the uncertainty of those variables. The only problem that we may need to take into account that if we are inverting our matrix H, we typically get a dense covariance matrix. So, and inverting this matrix so that we get a dense covariance matrix is a computationally costly operation. And as a result of this, we may want to also do some tricks here, only compute parts of this uncertainty if we need it. But if you need the uncertainty of the overall system, then that's typically the way to go. Again, there are some approximations you can do because you're typically only interested in the main diagonal blocks if you want to estimate the uncertainty of all the other variables with respect to one. And there are special ways to do this which are computationally more effective. What you also need to take into account is relative uncertainty. So quite often, especially if you look for loop closures, you want to actually say, what is actually my relative uncertainty of my current pose with respect to a certain previous pose? So you're not necessarily interested in a global reference frame, but what is my pose uncertainty relative to another pose in order to determine, is this a possible loop closure, yes or no? And the question is, how can we do this? How can we compute the relative uncertainty between xi and xj? And how we can solve this is that we actually compute the full matrix H. And then, let's say we want to compute the uncertainty of xj given xi. That means we can fix xi and make xi kind of our reference frame. And then say, given that xi is the reference frame, what's the uncertainty of this xj with respect to this reference frame? So we fix xi. So we don't optimize it anymore. We fix the variable by suppressing the rows and the columns corresponding to xi. And then we need to compute, in theory, the inverse of the whole matrix, and then take out the jj block from that matrix. But again, there are techniques where you can do this more efficiently. If you're only interested in a subpart of this inverse, there are ways for computing only this block jj of the inverse of the matrix. And then this block, this inverse, the block jj of the inverse actually gives you the covariance matrix of xj with respect to xi being fixed, and this tells you your relative offset. This is, for example, being used when you build maps. So this is one of the examples. The robot is currently here and computes the relative uncertainty of all the nodes with respect to its current pose in order to check which other nodes could be close to me, so I may inspect them for loop closures. And you see kind of the robot sits over here, and there's just a very small number of nodes which it actually needs to inspect, because for all the others the uncertainty is too small because it has already built a high quality map so that it knows it doesn't need to look for loop closures to other places. And that's one way where this uncertainty information is important if you want to decide at which other positions you want to check for loop closures. And this actually brings me to the end of today. So what we have introduced here is kind of the back-end part of the SLAM problem using a least squares approach of this graph-based SLAM, or even a special variant, this post-graph-based SLAM problem. A post-graph is again a graph which only contains the poses of the robot and doesn't take into account landmark features as a general SLAM graph should actually do. And we have discussed how we do this, how we can use the ideas of least squares in order to formulate that problem, how we can actually build up this matrix H and the vector B that are needed for solving the system. And the key insight in here was that H is a sparse matrix. And if H is sparse, we can actually solve that in an efficient manner. And so this is one of the key practical important insights in order to solve this, even for large systems having thousands, 10,000s or millions of variables. Otherwise, that would be computationally not feasible, at least not for building online systems. And this idea of postgraphs is something that you find today in a large number of different SLAM systems, also partially in localization systems today, where the informations are used to build up this graph, this postgraph online, and then the graph is optimized, sometimes only parts of the graph, only the recent history, some in an approximated fashion, some using hierarchical setups to save computational resources in order to tackle online computations. Some approaches use smart outlier rejection techniques to deal with unknown data associations. So there's a large number of variants that you may need to take into account, but the overall core part of this is actually very similar of those algorithms to what I have presented here. And there are also libraries out there such as G2O, GTSEM, or Ceres are the most popular three ones, which can help you to perform those optimizations in an efficient way. But here in that course, in the practicals, we're actually trying to build that system completely on our own so that you're actually able to get hands-on experience how to build such a system and do the homework assignments, and you can actually play around with your own 2D SLAM system and build, for example, a postgraph-based SLAM system so that you can put hands-on to every part of the problem and are able to derive all the Jacobians from by hand, and at least for the 2D case, do this in a very easy fashion so that you can build your own SLAM system and understand it from the core. That's one of the things that will happen in the upcoming homework assignments. So thank you very much for your attention, and I hope you got an idea on how graph-based SLAM or postgraph-based SLAM works, and we will extend that in the future to more general postgraphs, robust optimizations, and other things. So thank you very much.